Hello Year 10. I hope you had a pleasant Easter break. Today we're going to look at strong and weak acids. This is higher material. You'll notice that on the Caboodle textbook on pages 98 to 99. To begin with, I'd like you to think about the following questions. What is a strong acid and what is a weak acid? Pause the video to have a little think about what I mean by a strong acid and what I mean by a weak acid. Let's see if your ideas then are right about weak and strong acids. Here is a little diagram. In purple is the undissociated or non-ionized acid HA. In orange you have the H plus hydrogen ion, which is dissociated. You also have in green a negative A minus ion, a counter ion, whereby HA, the undissociated acid, has been dissociated or ionized into hydrogen ions, H plus ions, and A minus ions. Pause the video and think about whether this diagram represents a weak acid or indeed a strong acid. Does this diagram show a weak acid or does it show a strong acid? Hopefully you've looked at this diagram and realised that there are a great number of undissociated, non-ionised acid particles, acid molecules. Therefore, this is a weak acid. There are only a few dissociated hydrogen ions, right, ionised hydrogen ions, and equally the same for the counter ions. That means that this diagram represents a weak acid. So on the left hand side here I've got some ethanoic acid. You can see that on the bottle it tells us that it's 0.1 moles per decimeter cube, 0.1 molar. And on the right hand side I've got some hydrochloric acid, which is also 0.1 molar. So what we're going to do first of all is take some universal indicator and we're going to put a drop into some ethanoic acid and we're going to put a drop into some hydrochloric acid. And I'm just going to get, give it a bit of a swirl and put a bit more indicator in this one. And hopefully what you can see if I hold them up to the camera is that the one on the right is a far deeper red than the one on the left. How can that be? They're both at the exact same concentration. They're both acids. Surely we'd expect pH 1 like this one for both of them, whereas this one is more sort of like pH 3. Well, if we take a pH probe, and this is in a buffer solution at the minute, it's reading about pH 7. If I take this and put this into the hydrochloric acid, we can see that we're reading about pH 2-ish or so, whereas in this particular beaker over here, if I put the probe in this one and give it a bit of a stir, it's more like pH 3. The reason is that this is a strong acid, whereas this is a weak acid. That means that this completely dissociates into hydrogen ions and chloride ions, whereas this only partially dissociates into hydrogen ions and ethanoate ions. Here we have a simulation of what a weak acid would look like in solution if you could visualize the individual molecules. What we have here is we have a dark grey molecule which represents the undissociated acid, a red molecule which represents the hydrogen ion, and a blue molecule which represents the dissociated negative ion. And what we can see from this image is that most of the molecules are undissociated, that is to say the undissociated weak acid. This, by the way, is a weak acid of a 0.1 molar concentration. When we take some pH paper and place it into the solution, sure enough, just as we saw from the laboratory demonstration, it has a pH of about 3. When we keep the concentration the same, but change to a strong acid, This time we can see a dramatic change. Here now we have no undissociated acid. All we have are negative ions, dissociated negative ions in blue, and dissociated hydrogen ions in red. This time, when I place the pH paper in solution, we find that we have a pH of about 1, showing that this is for a strong acid. Strong acids have low pH, weak acids have higher pH, despite the same concentration, because strong acids completely dissociate in solution, whereas weak acids only partially dissociate in solution. We can view that in a slightly different way. We can show it with a graph. This is the graph for the strong acid, showing that we have the same concentration of dissociated negative ions and dissociated hydrogen ions. When we change that across to a weak acid, we find that we have a large concentration of undissociated acid and a lower concentration of hydrogen ions and dissociated negative ions. Strong acids completely dissociate, weak acids only partially dissociate, as shown by this particular diagram. The difference then between weak and strong acids is as follows. A strong acid completely dissociates or completely ionizes when it's dissolved in solution, when it's dissolved in water. From the laboratory demonstration, we saw that if I take hydrochloric acid, which is usually a gas, and dissolve it in water, it will completely ionize into hydrogen ions, aqueous hydrogen ions. Aqueous, remember, means dissolved in water, aqueous, and chloride ions. It is completely dissociated. There will be no undissociated acid in a strong acid when it's dissolved in solution. Conversely though, weak acids will only partially dissociate or ionize when dissolved into water. So as we saw from the video, we have ethanoic acid, which is a weak acid. It is a liquid at room temperature, but it only partially dissociates into the ethanoate ion and hydrogen ions. This reversible reaction means that the equilibrium is heavily shifted over to the left-hand side, meaning that most of the molecules, most of the particles in a solution of weak acid are undissociated as opposed to dissociated. They are unionized as opposed to ionized, as illustrated in the previous diagram. Please pause the video and make a note of this specific set of examples. This is important. You need to know both of these definitions. Okay, hopefully you've made a note of this already, but this is really just to hammer the point home. Here, in this diagram on the left-hand side, we've got a diagram representing a strong acid. It is completely dissociated. The red particles here are hydrogen ions. The purple particles here are the negative counter ions. So this acid is completely dissociated. That results in a low pH, a much lower pH than a weak acid. Conversely, weak acids are only partially ionized when dissolved into water. That means that there are a lot of undissociated molecules when you dissolve them into water. Here is a dissociated hydrogen ion in red and a dissociated negative ion in blue. Where they're combined, that's undissociated, that's unionized. That results in a much, much higher pH compared to strong acids, as we've now seen from both our experiment in the laboratory, our demonstration, and the animation I've shown you previously. Please can we make sure that that is written down nice and neatly in your exercise book. Here's a little table then, Year 10. This is a table showing the concentration of hydrogen ions in standard form in moles per decimetre cubed,
Notice how here this says per. This means that the unit here is moles per decimetre cubed. And it goes from 1 times 10 to the minus 1 all the way down from 1 times 10 to the minus 5. It then has in a separate column a pH value which corresponds to the concentration of hydrogen ions. What do you notice? Can you copy out this table, please? Can you think about what these numbers mean? What do you notice? Okay, here's that same table again. This is the pH scale and orders of magnitude. Hopefully what you noticed is that as the concentration of hydrogen ions increases by a factor of 10, so this is going down by a factor of 10, this way is going up by a factor of 10, 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 the pH value here increases by 1 unit. So when you've got a pH of 5, that has 10 times less the concentration of hydrogen ions as a pH of 4, or vice versa. You could think about it being there are 10 times the number of hydrogen ions in a pH of 4 compared to a pH of 5. Or, as written in this bullet point here, there are 10 times the number of hydrogen ions in a solution of pH 1 compared to a solution of pH 2. If I compare a pH of 3 to a pH of 1, the difference is by a factor of 100 because it's 10 times by 10. Equally, if I compare the pH of 4 and 1, that's out by a factor of 1,000, 10 times by 10 times by 10, which is 1,000. And between a pH of 5 and a pH of 1, that's out by a factor of 10,000. There's a difference by a factor of 10,000 because it's 10 times by 10 times by 10 times by 10, which is 10,000. Here's a diagram that represents that rather visually. This is the pH scale here in the middle, as we saw in our last lesson in terms of neutralization in the pH scale. The pH scale runs from 1 all the way up to 14, 1 being a strong acid, 14 being a strong alkali. Somewhere around here, 10 and 9, these are weak alkalis, these are weak acids. So the higher the pH, the more basic or the more alkaline the solution. The lower the pH, the more acidic the solution, with a pH of 7 being neutral, that is to say pure water. Neutral is neither acidic nor alkaline. Basic is alkaline, acidic is acidic. And it's got various different examples of different things you can find around your house with their various different pHs on. What you'll notice is that as you increase the hydrogen ion concentration, you end up with a lower pH. And what you also might notice is that this is the pH in standard form, 10 to the minus 14, where you've got 1 times 10 to the minus 14, that will give you a pH of 14. So all you need do to work out the pH, if you've got the hydrogen ion concentration, if it's 10 to the minus x, that will be a pH of x. So for example, if it's 10 to the minus 5 in terms of the hydrogen ion concentration, that will give you a pH of 5. Or 10 to the minus 4, that will give you a pH of 4. Hopefully, together with the previous slide with the table which you've copied out nice and neatly in your notes, this makes perfect sense. As a bit of extension year 10, I'm going to give a link in the description to an excellent video on acid-base reactions in solution. A really fantastic video from a YouTube channel called Crash Course Chemistry. This is video number 8, but as I say, I'll leave a link to this in the description in the YouTube on this particular channel, on this particular video. As a bit of extension, I'd like you to make a mind map of the various topics from this video on acids and bases, from this particular video. Some information will of course be a recap and some will be new. I'd like to state though that this video is quite high level. It almost borders on university level chemistry. So just glean from it what you can, because this is a nice little summary. This will lead to a nice little summary on acid and base chemistry, which essentially has been the bulk of C5. I'll also set for you some questions in Educake which will form this week's work. Thank you ever so much for listening. As ever, if there are any problems Year 10, please don't hesitate to get in touch. Have a great afternoon and a great day.